What happens when we hand over the construction of physical matter to artificial intelligence? For centuries, science has relied on the Edisonian approach. It is an empirical strategy characterized by brute force trial and error experimentation to find the specific combination of elements that yields a desired result. To develop the incandescent light bulb, Thomas Edison manually prepared and tested thousands of physical samples, relying on intuition and existing literature to guide each successive attempt. This manual process is slow. It takes an average of 10 to 20 years to transition a single novel material from initial laboratory discovery to widespread commercial production. Even at the time, this was seen as inefficient. Nikola Tesla famously remarked that a small amount of theory and calculation would save Edison 90% of his labor. Today, this decades-long timeline cannot keep pace with the urgent deadlines of the clean energy transition. We require a method that moves faster than human hands. Achieving a net-zero future requires specific breakthroughs in solid-state batteries, high-efficiency solar cells, and carbon capture systems. These technologies require complex chemical combinations, often involving 3 or 4 different elements. The number of possible structural arrangements in this chemical space is mathematically staggering. A human researcher can only explore a tiny sliver of these possibilities over an entire career. Most of the potential solutions remain hidden in the void of the unknown. Humanity is running out of time. To meet modern technological needs, we can no longer afford to guess our way to the next discovery. To bypass the limits of traditional screening, researchers are adopting a strategy called inverse design. This process reverses the scientific method. Instead of testing materials to see what properties they hold, researchers define the exact physical traits they need, like high ionic conductivity, before the material even exists. Generative AI models then construct novel atomic structures from scratch, building a geometry that satisfies those specific target prompts. With the diffusion model, the system takes a stable crystal and progressively adds Gaussian noise until it is completely randomized. To generate something new, it reverses that process, refining a random starting point into a stable, novel geometry based on user requirements. By working entirely in a digital environment, this inverse process can simulate millions of candidates in the time it once took to test a single physical sample. The scale of these AI-generated discoveries has already surpassed the total number of materials identified by humans throughout history. Here are 6 distinct crystal structures discovered computationally by the genome model, ranging from optical materials to potential superconductors. In a matter of days, models have predicted the existence of millions of theoretically stable materials. However, possessing millions of digital blueprints is only the first step. If human hands cannot build them fast enough, these discoveries remain trapped in the computer. Moving from a digital prediction to a tangible material requires a transition into the physical reality of a laboratory. This is the A-Lab, an autonomous facility where artificial intelligence guides robots in the physical creation of new materials. Robotic arms mix powdered precursors, press them into pellets, and move them into furnaces, executing the entire synthesis workflow without human intervention. Using active learning, the system analyzes its own results. If a synthesis fails, the AI reviews the data and autonomously proposes an adjusted recipe, such as changing the temperature, to bypass thermodynamic traps. This automation of physical labor is the critical bridge that allows laboratory synthesis to keep pace with digital prediction. Despite these advances, a digital prediction does not always survive the transition to the real world. A major hurdle in translating these blueprints is crystallographic disorder. Generative AI models are trained on pristine, perfectly symmetrical crystal structures calculated at absolute zero. But in a physical lab, materials face heat and kinetic traps. Elements mix irregularly, creating structural chaos that deviates from the perfect digital model. This is exacerbated by a lack of negative data. Because failed experiments are rarely published, AI models inherit a human selection bias, making it difficult for them to predict when a material will fail to form. Mastering the translation from pristine theory to messy physical matter is the current frontier of the field. The solution is to build a closed-loop system where prediction and synthesis act as a single engine. By feeding real-world synthesis failures from the A-Lab back into the generative models, researchers can improve the accuracy of future predictions and account for structural disorder. A collaboration between Microsoft and the PNNL recently proved this loop works. They filtered millions of AI candidates to identify and successfully synthesize a solid-state battery prototype that uses 70% less lithium. This continuous feedback loop is successfully narrowing the massive gap between purely computational data and the messy reality of physical matter. As these autonomous workflows begin to account for the complexities of the lab, they move closer to making discovery a repeatable, targeted process. What future technologies become possible now that the materials themselves are being computationally targeted?